First, I would like to thank you for giving me the opportunity to present my work and work of my colleagues on today's presentation. Today I will speak about diagnostic tests for some specific type of circular regression models. I would like to say at the beginning that this research is supported by the bilateral cooperation project modeling complex data, selection and specification. First, I will give you the short outline of my presentation. In chapter 1 is divided into two parts. The first part is related to regression curve and its properties, and the second part is focused on probability model, which we will use later for distribution of angular errors. In second chapter, we will define the regression model, which we will use, and we will also see some properties for that model. Chapter 3 consists a testing hypothesis about the distribution for model innovations. In section 4 and 5, we will see some results for simulations and real data set applications. And after that, I will mention a subject of our current work and also some possible directions for future works.
Katarina, may I just stop you for just a second? Is it possible to open the screen if you have the possibility? Your face is not seen, just very minor probably, but if not, just continue.
Is it okay now?
We do not see you, but maybe continue. We still do not see you. I do not, at least.
Okay.
Just continue and maybe put it full screen.
Do you see my presentation?
Just put it full screen. Yes. Great. Thank you. Please continue.
I don't know what is the problem. Okay. Let's consider the regression curve of the following type. Covariate U is a point from unit circle, and the parameters beta 0 and beta 1 are complex parameters with the restriction that parameter beta 0 is on the unit circle. In the situations when module of beta 1 is different from 1, we call this mapping Mobius transformation. We know that Mobius transformation is one-to-one mapping which carries unit circle onto itself. Now just a short reminder about Mobius transformation. It is obtained by a composition of translation, rotation, homotheties, and inversion. And from this mapping, we can see that we can interpret this parameter beta 0 as rotation parameter, but the interpretation of the second parameter beta 1 is a bit more complicated. We can see that parameter as parameter that attracts the points on the circle toward the beta 1 divided by module. And from one concrete example, we can see that with increasing module of beta 1, the first case is case with module 1, the second with module 0.3, and so on. We can see that with increasing this module, the concentration of points around the beta 1 scaled with module is also increasing. Now we will move on probability model of angular errors. Let's consider a random variable x defined on a unit circle in a complex plane. If its probability density function is given by this expression, we can say that x have a wrapped Cauchy distribution with location parameter mi and concentration parameter delta. From these figures, we can see how a density plot looks like for different values of location parameter and concentration parameter. Changing the location parameter we move a peak of distribution toward the circle, and by increasing the concentration parameter delta, the peak of distribution also increases, and the concentration of points around the location also increases. For our purpose, we will assume that location parameter is equal to 0, and we will use appropriate notation. Wrapped Cauchy distribution has some nice properties. It is closed under rotation. It is closed under product for two independent random variables, and it is also closed under Mobius transformation. That is very interesting. And in situation when concentration parameter is equal to 0, Wrapped Cauchy distribution turns to uniform distribution to the circle. Now we can see the regression model which we will use. This model is first proposed in the work of Kato et al. The covariate x and the parameters beta 0 and beta 1 are defined as previously, and angular error epsilon follows Wrapped Cauchy distribution with concentration parameter delta. Smaller value, in this case, smaller value of this parameter indicates the less concentration of the error variable in the model. Based on properties of Wrapped Cauchy distribution, we can obtain the conditional distribution of y given x, and this distribution is also Wrapped Cauchy, now with some parameter delta, which expression is given on the slide. Now we want to estimate the unknown parameters of the model, but the problem is that we can't use standard results for ML for Wrapped Cauchy distribution, because now this parameter of the distribution depends on covariate x. And the idea is next. First, we transform covariates and responses, and also transform parameters beta 0 and beta 1 into polar coordinates. Now we have four unknown parameters. We have parameter theta 0 and theta 1, which are arguments of the beta 0 and beta 1, respectively. Rho is modulo beta 1, and the fourth unknown parameter is parameter delta, which is parameter from distribution of angular errors. To give the estimates for these parameters, we maximize the log likelihood function, which expression is given on this slide. And under standard regularity conditions, these estimates have an approximately normal distribution. Now the residuals of proposed model are given by argument of quotient between responses and predictors. Okay, now we are interested in testing goodness of fit of the null hypothesis that residuals follow Wrapped Cauchy distribution for some concentration parameter delta against the alternative. And for testing this hypothesis, we use several tests. The first two are classical ones, Cooper and Watson tests. These two tests are rotation invariant of Kolmogorov-Smirnov and Kramer-von-Mises test statistics. And both tests are based on difference between empirical and theoretical distribution function. The third test is proposed in the work of Yamal-Madaka et al. Test statistic is defined like L squared weighted L squared type of distance between empirical and theoretical characteristic function. And in the case of Wrapped Cauchy distribution, the theoretical characteristic function is defined on the slide. I would like to underline here that in the case of circular random variables, theoretical characteristic functions are always defined only for integer values. That is the consequence of the fact that circular random variables are invariant to adding 2 pi. And for this test statistics, Cooper test, Watson, and also for a test proposed by Rao-Yamal Madaka, all 3 tests are not distribution free. So we use warp speed bootstrap algorithm to perform sizes and powers. This algorithm works as follows. First, for fixed covariates, we simulate a sequence of angular errors and the corresponding responses. Based on these values, we can compute estimators of the unknown parameters and also to calculate residuals and the appropriate value of test statistic. After that, we can generate a bootstrap sample y star, where now the angular errors follows Red-Cauchy distribution with estimated parameter. Based on that values, we can obtain bootstrap estimates of the unknown parameters, residuals, and the value of bootstrap test statistic. We repeat this procedure n times and get 2 sequences of test statistic. For each sample, we reject the null hypothesis if the value of test statistic is greater than appropriate quantile, which is obtained based on empirical distribution of the bootstrap test statistics. In our simulations, we used 10,000 resamples in the warp speed procedure. Also, we consider sample sizes 25, 50, and 100. For alternative distributions, for model innovations, we used rep normal for Mises, cardioid, Cartwright power of cosine, Jones-Pusey, and Bachelor's distribution. The first 3 distributions are quite standard when we considering circular random variables, and the last 3 are some kind of generalizations of these 3 distributions and wrapped Cauchy distribution. On this slide, we can see the probability density functions for wrapped normal and for Mises distribution. These 2 distributions performs quite similar. And for fixed concentration parameter, for wrapped normal distribution, we can see appropriate alternative for parameter k in for Mises distribution. Okay, on this slide, we can see how density plots looks for location 0 and different values of concentration parameter. We consider wrapped Cauchy, wrapped normal for Mises and cardioid distribution. In the case when concentration parameter is small, 0.1, and if we calculate appropriate value for the parameter k in for Mises distribution, we can see that in the case with small concentration parameter, all distributions perform similar. But in the case when we increase concentration parameter, we can see that the peak of distribution dominates in the case of wrapped Cauchy distribution. On this table, we can see estimated type 1 errors in percentages for different sample sizes, 25, 50, and 100. And we can see that all tests are well calibrated. From the empirical powers, we can see that with the increasing sample size, the powers for each test is increasing. And we can also see that test statistic Tn performs better than classical ones, classical twos. And also for increasing sample size, the difference between powers of tests Tn and the classical ones decrease. The results are similar also for other alternatives. With increasing sample size, powers are also increasing, and in general, Tn performs better than classical tests. Now we will move to real data set examples. The first example is related to wind direction, which was measured twice daily for 21 days. The idea is to predict the wind direction at noon based on values at 6 a.m. And the plot from the left figure, we can see that we have 5 outliers, and removing that observations from the consideration, we can plot the spoke diagram. On this diagram, the points on the smaller circle presents predictors, and the points on larger circle responses. If this distance is smaller, that means better prediction. In this case, we can see that we have a few good predictions, but also a few not so good predictions. And that is reflected also in p-values, where 2 tests accept the null hypothesis and 1 not. In the next example, the situation is different. In this example, measurements for 2 successive diastolic blood pressure were taken for 10 medical students, and the idea is to regress the diastolic blood pressure based on previous measurements. We can see from the plot of circular distance that there is no outliers, and also from a spoke plot we can see that all predictions are quite good, which is in concordance with the empirical p-values. And the last example contains data set with 35 peak expression times of synchronized genes common to heart and liver tissue in vivo. And the idea is to predict peak expression times related to liver based on peak expression times related to heart. From the plot of circular distance, we can see that 1 point is outlier, and from spoke plot we can see that we have a lot of good predictions, but also a few wrong predictions. But based on sample size, we can see that this model performs quite good, which is also reflected in the p-values. I don't know if I mentioned, but for circular distance, here we use the half of 1 minus cosine of difference between response and predictors. Now we will move to asymptotics of test statistics Tn. Let L squared denote the separable Hilbert space for all infinite sequences of complex numbers, such that weighted sum of squared modules is finite. If we define inner product and norm on a standard way, then under the null hypothesis and some mild regularity conditions, we can say that there exists a zero mean Gaussian element with covariance kernel, such that test statistic converge to norm of that Gaussian element. We are currently working on finding the exact expression for the covariance kernel, and also to find all regularity conditions under which this theorem will hold. Of course, the IID situation we can obtain from the work of Yamala Madaka. And some possible ideas for future works. The first idea is to propose and consider some other tests for testing goodness of fit with abrupt Cauchy distribution for model innovations. And the second idea is to consider some multiple circular regression models. Some of them are proposed in the work of Jan Biswas, and these 2 multiple regression models are presented on the slide. That is it.